Hello, hello, hello. This is Nicholas once again on this lovely Thursday afternoon, wanting to finally talk to you today about the Cauchy integral theorem. Now, having done Green's theorem and having done Cauchy-Riemann equations, we're ready to state and prove the Cauchy integral theorem, which is a really powerful result with a lot of strong parallels to standard Calc 3 material. So we first have to talk about what it means to integrate a complex function. And our region that we're going to be integrating over is what's known as a contour. Right, this contour is in the Argand field, the complex plane. And, it might be something like that. It might be some path that would be open, or it could be something closed, right? And Cauchy's integral theorem deals with closed regions. So if this is our, it would be oriented the other way. If this is our closed region with boundary delta D, region D, and f of z is in D, now we have a couple conditions here. If f of z is holomorphic, in other words, analytic, in other words, we can make a Taylor series for f in D everywhere on and inside D. So being holomorphic on the boundary is important too. The curve, the boundary curve delta D is, of course, closed, right? And it's simple, meaning it only intersects itself at its endpoints. And C, or the boundary of D, only has a finite number of corners. So something crazy like a Weierstrass function would not be suitable, but like a pentagon would. If we have those conditions, Cauchy's integral theorem is very simple. It says that the contour integral over the boundary of D, I don't know why I keep using C, over the boundary of D of f of z equals 0. And now the contour integral is just a special case of the line integral, and we just basically call it that when we're reserving line integrals over curves or over boundary curves when that boundary curve lies on the complex plane. We just call it a contour integral, but mathematically it's done the same as a typical line integral in Calc 3. So if f of z is u plus vi, and dz is dx plus I dy, then the contour integral, and I draw this little circle around the integral to say that it's a closed contour integral. In other words, it's like over a loop, our region is closed, of f of z dz, that's the contour integral of u plus vi times dx plus I dy. That's equal to the contour integral over c of u dx minus v dy plus I times the contour integral over c of v dx plus u dy. And that's just foiling out from the algebra there. Now we're going to deal with these two integrals here and show that each one of them evaluates to 0. So the first integral I1, which I'll call this integral right here, is line integral over, or the contour integral over c of u dx minus v dy. And the second integral is contour integral over c of v dx plus u dy. Okay, and since these functions are holomorphic, everything is nice within the region, right? The partials with respect to x and y of u and v, right? They're going to exist and they're going to be continuous. And our region is simple and closed. Our boundary is piecewise smooth. We have all these conditions met. We can use Green's theorem on each of these curves. And I kept using C. I'm sorry. By C, C is the boundary curve of D. Anyway, so when we use Green's theorem, right, this is like P and Q of our vector field and P and Q. And so we get the double integral over the region D of the partial of Q with respect to X, which is the partial of V with respect to X, minus the partial of P with respect to Y, negative, minus the partial of P with respect to Y, which is the partial of U with respect to Y, dA. And then for the second integral, we get over D of the partial of U with respect to X minus the partial of V with respect to Y, dA. Now, remember from my very last video on the Cauchy-Riemann equations, right? The partial of U with respect to X equals the partial of V with respect to Y if F is holomorphic on and inside the boundary curve. And the partial of U with respect to Y equals the negative of the partial of V with respect to X. And so both of this fact about the complex differentiability makes, right, these are the same and these are the same. And so they just cancel out and the integrand is 0 and the integral is 0. And so the whole integral, the whole contour integral over the boundary curve of f of z is 0. And that's a really neat result. Now, I just want to say a couple things about the parallels here to what you would learn in a standard Calc 3 class, right? If we're taking the line integral over C of f dot dr, and f is conservative, and C is closed, then that line integral is 0. Just like how, if we're taking the contour integral over C of f of z dz, and we say f is holomorphic, and C is closed, then that special type of line integral is 0. And so basically what I'm getting at is the condition for the vector field being conservative in vector calc is akin to the condition for this scalar valued function f of z being holomorphic, in other words, being analytic. There is strong parallels, right? And so with that,